Be the lecture comprising 4.8, 4.9, and 4.10 for October 12 and 13, Monday, Tuesday of this upcoming week, followed by finishing Chapter 4 and starting Chapter 5 live later in the week. Found out in the meeting that some people are behind, some people are ahead. They're actually into Chapter 5 already. And so the hope is still to get to chapters 4, 5, and 6 for the second test, and then to get to chapter 8 by the end of the class. So that is the plan as we're seeing it. Not everybody was at the meeting, but that's what I heard, and that's what I'm going to have to assume is true. Okay, meanwhile, let's get to some of this stuff here. Looks like we have one short section, 4.9, and a couple of medium length sections as well. Let's go back to where we were explaining the variation in thumb length using the variable sex. Thumb length, the variation in thumb length is the variation of sex and the variation of other stuff. Looking at the histograms and scatter plots of this word equation, showing the overall variation in thumb length could be partially explained by taking sex into account. So they have some of the R commands involving a density histogram, the variable thumb, and from the data set and the colors they like and all that. So they even put in for the point graph, just a point graph, the various color orange size 5 and transparency alpha 0.5. So I like the first group better, although I don't prefer orange that much. But this group says the same thing. It says that males, if you look here, males are born with bigger thumbs. And you can see it's shifting towards the right here on the density histogram, but it also shifts upwards over here on the point diagram. So it's really two different ways of saying the same thing. So can't seem to maximize the picture today. I'm not quite sure why that would be. Let's click on that. Maybe I can stretch it out a little bit. Maybe that'll help a little bit. Okay, so we can get it maximized. Okay, that's better. That should be better, but not too maximized. Sorry, this doesn't work very smoothly. Okay, let's see if we can do the same thing with height. Instead of gender or sex, we can try height and replace sex by height. It seems like taller people might have bigger thumbs. Let's just test it out. Do you think we could explain some of the variation in height? Could we use the same approach? I'd say absolutely yes. It seems logical that taller people might have bigger thumbs. We could actually choose the same approach, of course, and first we need to recode height as a categorical variable, and so we could reconstruct the new variable by cutting it up into two categories, short and tall. Which of the functions might help us recode height as a variable with two levels? This one I really shouldn't tell you the answer for. I'll be honest, I'd forgotten the answer too, but I'll let you dig around and see if you can find it. We'll be using it soon enough anyway, but this one I'm not going to just give it to you. So as I shrink it down just a tiny bit, man, this just doesn't want to go very well. Write some code to cut height from the data frame fingers into two equally sized categories. People below the median height and people above the median height. And save these categorical categories into a new variable called height2 group. Label them short and tall, even though some of them are very close to the median height. So here, the command to put it into this new long-winded variable name, fingers $height2 group, we'll use the command ntile, and we'll put in the variable fingers where is that? Yeah, fingers $height, comma 2, and that gives us two different groups. And I should capitalize height because they do pay attention to that. Parentheses and capitalization, that kind of thing. Don't need that extra junk. Okay, modify this to label fingers $height to group appropriately. So basically we just have to take out sex and put in height. So that's what we'd have to do. And put it into the group. So it looks like we need to not only change it to sex, I've got Halloween music on in the background in case you can't tell. So let's make sure this is height to group, because that's what they chose to name it. They always pick the longest names they can. I'm just the opposite. I just pick the shortest names that make sense. And then we have factors. fingers $ sex, levels 1 to 2, labels as females and males, so that part looks pretty good. But instead of gender, we want to change this over to height. So let's take out sex and put in height. And then we'll put in, of course, short and tall, as they suggested we do. So I'll change that to short. I'll change this to tall. And since they had it like halfway done with a different set of numbers. And then at the end, head select, fingers, thumb, height to group. That one does look like it's going along pretty well. So they already had done that one for us. And of course the hint, use n-tile to split a variable into n number of parts, certain number of parts. That'd be 2. So that's why we picked 2. Later we'll do 3. Meanwhile, let's just go ahead and run this and see what we have. We have all of that. And for some reason, as I submit this, I can't seem to always get the titles in of the peoples, the height, that is, the short versus the tall. And notice I have not available, and it should be saying them. It should have tall and short. Why didn't I get that done? I had a little trouble with this before. Seems like I'm still having it. And so at fingers height to group, n-tile, fingers $height 2. And I believe that's, as I look over here, that is exactly the same as I had before. The slightest change will make a difference. Now here we have factor for fingers $height. And I've got factor fingers $height. And I'm kind of, oh, there's group, height 2 group. Lovely. So I got to put that in. 2 group. The rest of it seems to be there. And then the levels, as I check the solution out, see, okay, they're doing it the old-fashioned way. Parentheses 1, comma 2. You can do colon 1. That actually doesn't make any difference. So it looks like all the rest of it is probably in there. So now if I go ahead and run this, let's see what happens. Ah, there we go. Now if I remove this little hint, it's hard to remove that. The screen is magnified too much. Maybe I should just shrink the screen down. It doesn't seem to work the other way. So now it seems to be working. So I just typed in the incorrect factoring variable. My fault. Now we can try looking at the data the same way as we did for gender. If we created a grid of histograms for thumb based on height to group, what would you expect to see? Well, you'd probably see smaller thumbs amongst the smaller heights. And scatter plot, well, scatter plot's the same. You know, if you had the histograms, one histogram would be a little lower than the other, be up a little higher on the other side for the males. And same with the scatter plot, you'd have a little lower on the left versus on the right. So it's very similar answers to those. The higher numbers will go up a little bit higher, and you've got separated by not gender, but by short versus tall. So the tall people would tend to have, or predicting, bigger thumbs, which turns out to be absolutely true. So create histograms in a scale, in a grid, and scatter plot to look at variability in thumb based on height to groups. So let's see if we can do that. It's definitely going to be a histogram command. It looks like they want a density histogram as well. So I'm going to go ahead and put that in. GF_DHistogram, or density histogram. And then we continue and type in the variable with a tilde on the thumb. And it also says that the data comes from fingers, because they constantly forget where it's coming from. Anyway, and then we can continue with a chaining situation that's good outside of the parentheses. So this is going to be % greater than %, which looks like a contradiction to me, but that's just how they chain it. Got to make sure the greater than sign is there. So that's there. So I can go to a second line and continue with this and talk about the facet grid. GF facet _ grid gives us a special kind of look. And we can look at the height to group. I have to admit I'm a bit distracted by all these long variable names. I'm not used to that. And then we can continue and look at GF point, and that would be the scatter plot. So I could just put this under here. Actually, the green messages don't really mean anything. They're meant to be help for us. So we can look at GF_ point, and then look at the thumb tilde height. So that's always y, then x. So y is thumb and x is height. So x will be explaining the thumb length. The height is supposed to explain, not the other way around. The height will explain the thumb. So it's always y, then x. And to be clear, that's going to be height to group. So we have to make sure that's in there. And then data equals fingers, because they already forgot that's where the data came from, I guess. Okay, let's see if that's going to be enough for us. Of course, we could look at the hint, as always. Don't forget to use GF Facet Grid to put your histogram in a grid. So we can run it, and we can see how that, let's see if we close that up. We can see how they just gave us one. They forgot to give us the histogram. And I can't remember why. It did give us the short versus tall. And looking at that part, which I apparently did successfully, I just didn't enhance it with the colors and the widths and all that. The tall people do tend to have numbers aiming up a little bit higher than the shorter people. Not surprising. Now, I'm a little bit bothered as to why I couldn't get the histogram to run. I must have slipped up on something very small, but I can't seem to find out what it is. So if I run this, oh, okay, maybe, no, I need to submit it. Then it'll give me some comment. And did I call it GF histogram? Well, I thought it was D histogram. But anyways, just look at the solution, see what I might have done differently. Maybe I did D histogram. Okay, so maybe if I go back to my script and take out the D, would that be enough? Okay, let's just see if I can run that. And let's see now. If I close this up and go to previous plot, no, it doesn't want to do histogram, so I have to see what the solution has in store for me. Okay, so if we take a look at the solution, it's saying that GF histogram, tilde thumb, data fingers, tilde thumb, data fingers. This can drive you crazy, I know. GF Facet Grid, height to group. And I forgot to put in tilde dot. Yeah, so tilde dot, and that kind of tells you that that's the Y group, and the dot is like the former X group or whatever. And I'm sure that's all there is to it. So now I can just run that. And now I'll feel a little bit more comfortable once I erase this part, go to the previous plot. Yes, there are my histograms, finally. It's just something subtle. That's the thing about programming. They have to be absolutely exact. That's why I'm a math major. We're kind of the same way in a lot of ways, but it's not quite the same type of thinking, which I do prefer a lot. But oops, now where did that go? Why does it do weird things like that? Well, you breathe on it wrong and it just disappears. So let me go back to where I was. Yeah, so we got it to run. We can kind of see that basically the tall people are moving slightly to the right of the short people, although I would not call that a significant difference. The Facet Grid did give us an ability to compare at least two different groups of people from the same overall data set. So there was a lot of variability within females and males, and a lot of variability between short and tall groups. It doesn't guarantee that if you're a tall person you have a large thumb. It doesn't guarantee that. Just the tendency is all. There's less variability, though, within each group, which is good. We like to get rid of variability. And but there's less within each group than if we looked at the whole thing. So anyway, we have that kind of thing going on. And we can also try looking at these distributions with a box plot. And we can create box plots of thumb by height to group. So let's see if we can do that. Let's look at the hint. And GF box plot, of course, will do that and without a grid. So let's see if we can figure out how that would work. I'll go over here and GF underscore box plot. And then we can continue with the Y variable thumb matched with the X variable height, not just height, but of course height to group. Why not just toss in several other words at the same time? And then we'll make sure that we remember, because it's easy to forget, that data equals fingers. Okay, there it is. It's all in there. And that might be enough. Let's hope so. Let's run it and see what happens. It is amazing. So we have our two box plots. It's a little bit squished in this little plot area. And yet they do not give us another reflection of it. So this is kind of saying the same thing. Oh, why does it do that? There's something really wrong with this now. All my technology is failing at once. It's been a rough couple of days. So let me see if I can get back to 4.8. And something, I must have bad karma today. The computer doesn't like me. Okay, let's see where we left off. Well, they did have the box plot switch, although we don't have it anymore, but we do notice that it is similar to this. The shorter people had a little bit lower smaller thumbs than the larger people, and the box plots spell the same thing out in a different way. So based on what you see in the histograms, scatter plots, and box plots, is some of the variation explained by height? Absolutely yes. That was the whole point of doing this. So we can break height into three categories. Let's call it height 3 group, and compare the distribution of height amongst all three categories with a scatter plot. Let's see if that could work. And now we're going to talk about fingers $ height 3 group, which they got us started on. They have n-tile, fingers $ height, but of course we have to change that over to 3, not 2. So this will be kind of a middle group, or average group in between. And we have to reflect that over here by talking about the 3 levels, 1:3, or you could just say, the other way of saying it was what, C parentheses 1, 2, 3 parentheses. So you could do it that way, but this is a little bit shorter. And they didn't really tell us which way to go. I think they're going to say average. You could say medium or something like that, but I'm going to use average, put that in parentheses in the quotes, and there we go. And I think that should be enough. Now we need to also get the scatter plot. That's the GF point command. I like the box plots personally, but GF point does something different. And then we have thumb, tilde, height, and then we continue. Let's actually height 3 group. I always want to stop with height. I shouldn't do that. Height 3 group. You have a height 7 group if you want. And then, of course, data equals fingers, because we cannot forget that. And if you don't write it down, it's not going to understand where the data comes from. And we also need to do the box plots. So let's see if we can get to another line and talk about GF underscore box plot. And then we'll have exactly the same stuff inside. So let's just go ahead and copy that. Tired of writing it down over and over again. So I'm just going to slip that inside and Command V. Okay, so that's all in there. And let's go ahead and run that. We should have 3 different things to look at. And okay, boy, things are not going well for me today. It doesn't have anything, so I must have missed something, some key ingredient here. What could I have missed? Maybe some of you already know, because some of you are doing better than I am, I'm sure, on this stuff. I guess I'm going to have to just run it and just check the solution. That's something I'm not proud of doing, but it doesn't seem to want to let me look for a solution this time. Well, that's not too cool. And I don't want to waste your time looking for the smallest mistake that I must have made here. But maybe this levels 1 to 3, maybe that would do it. Okay, you've got n-tile for the first line. Then you've got, okay, and then factor for the second line. And that's fingers, $ height group. I didn't put that in. Oh, brother. So, yeah, this is probably the most difficult section I've had to do so far. It took me a while to get ready for it. And as you can see, I should have spent even more hours getting ready than I did. So this is something that I do not find particularly easy or obvious. Height 3 group. I think that should take care of it with these very long variables that they're very, very fond of here. Okay, fingers height 3 group, and then maybe that's enough. Let's just cross our fingers and hope it works. Okay, it doesn't seem to work, so I give up. It doesn't let me have a solution either, which I've got to submit it first. That's why. So they give me some stuff that sometimes helps and sometimes doesn't. Let's just go ahead and see if it'll give me a solution. No, it doesn't want to give me a solution. So let's just go ahead and look and see what happens. Hopefully you've had more luck than I've had. Here is the scatter plot. As you can, why does it go away? I'm starting to get a little bit ticked at this. Just wants to disappear on me. I really can't tell you what's going on. So there it is. Short people, smaller thumbs. Medium people, slightly bigger. Taller people, bigger thumbs. And there's the box plots. A little bit more visual. And we've talked about box plots before, but the median certainly is the most important number. And you can see that one on the steady rise as people get taller. Maybe I should just go to instructor view. Maybe it's not liking me in the student view today. Now we looked at the comparison between the 2 levels and the 3 levels. And the 3 levels seems to have more information in it. And the more levels you have, the more information there would be. So that's kind of like their main point here. Which height variable The three categorical variable or the two category variable explains more variation in thumb length. The three category variable, clearly. How can you tell? There's just more information. You've got more division and less variability. So the variability, if you were to take care to measure all this stuff out, variability is shrinking each time because you're getting more and more specific. That's the main idea there. So would it explain even more variation here, saying the same thing again? Yeah, it explains. It just kind of takes care of it. You're kind of carving it up, and if you divided it up into each individual person, then you'd have no variation at all. But that's the extreme case that nobody would do. But the more groups you have, the less variation there is. Why? Because you just have carved up better, more specific is a good word for that. So we get into another part of this long section. How we're going to get to chapter 8, I'm not sure, but they say we will. Up to this point, we've been using height as though it's a categorical variable. First, we divide it into two categories, then three. And we are throwing away some of the information we have in our data, they say. We know how many inches tall each person is. Why not use the information instead of just calling people tall, short, or average? That could be done. We could try a different approach, a scatter plot of thumb length by height, the exact height, that is. And we could try using GF point to do this. So let's see if we can do this successfully for a change. I have to admit, I've been saying it all along, I am not a programmer. I'm a statistician. And so this is the new way of teaching this stuff. So I'm trying to roll with the punches here. And I know some of you have not too much trouble with this. Others may have more. I've decided to emphasize slightly different things than some people are. But I'm going for what the tests cover, to be honest. There's a lot of other fun stuff to do. But if the tests don't cover it, a lot of students come to me, and rightly so, well, does this count for the test? And I have to say, I don't think it does, and I don't feel so good about that. I know as a student, I always wanted to know what the test would cover. And if the test wants to cover extra stuff, so be it. But if it isn't, if they're going to cover this kind of thing, then I want to talk about it, so I give you a fair shake. So sorry to ramble on for just a second. Let's try to get this done. I actually have a list of things I have to do after I'm done with this. So let's see. We've got thumb tilde height. That's y tilde x. And of course, not just height. It's height 3 group. So actually, this time it's just height. How about that? And then, of course, we always have to remember data equals fingers. Never can forget that. Seems like they would have that already taken care of. That's probably what the Jupyter notebooks do. They've got that stuff already packaged for us. So let's go ahead and just run this one. This should be a simple one for a change. Nope, doesn't seem to like me. I don't know what's going on. I just don't know what's going on. So I submit it, and have you called? Yeah, I did GF point. Did I give the correct results? Have you tried using GF point? Well, yeah, I did. I used GF point, and it worked last time. Good thing I'm not doing a live lecture on this. This is good enough to get this out of the way. Well, anyway, when it finally does run, let's see if I got it the first time. Probably not. Previous plot. Nope. I don't know what's going on. Probably something really easy, but I don't know what it is. Okay. Anyway, here's a Puron scatter plot. So several steps later, we see that here's the height measured probably in inches. Yeah, it looks like it's in inches. And here's the thumb length in millimeters. And so usually the smaller people, shorter people have smaller thumbs, and the large people tend to have wider thumbs. But there's a lot of variability, as you can see. It's just a tendency. But that has a lot more detail than before. Okay, now the scatter plot above shows thumb as the outcome variable on the y-axis and height as the explanatory x variable. Which of the following relationships can you see in the graph? Taller people have longer thumbs. Yeah. Shorter people have shorter thumbs. Yeah, we just said that. See, if you know someone's height, you can make a more accurate prediction of their thumb length than if you didn't know their height. Yeah. But are the students still growing? I don't know. Is there no pattern in the relationship? We just talked about a pattern, so I hope you're not picking those two. Now they've decided to group it by different groupings, short, medium, tall. Okay, and it's a little unclear as to how they did it, but they grouped them, and these are kind of like part of a box plot, I guess. You're not responsible for this. They're just trying to make a point, and they're showing that generally they get bigger as you get taller. And this is trying to relate it to the prior example when we had 3 different groups. So this is how it goes. Yeah. So each box corresponds to one of the 3 groups of our height 3 group variable. On the x-axis, you can see the range in height for the 3 groups. Why do you think the box for tall is wider than the box for medium? Well, height varies more for people in the tall group. And yeah, height just simply varies more. And as you can see that, yeah, I've got some people have very big thumbs and some people that don't really have very big thumbs. A lot more variability here. Look at the short group. Well, I guess technically this is part of the short group. It's still, it looks like the tall still has the edge on that, but not by too much. Because we used n-tile, we divided our group into three groups of basically equal sizes. Most people are clustered around the average site. It makes sense that the box in the middle is the narrowest because we had more people in there. If you count up all the dots, that's the middle third, so it's a bit narrower and a bit stretched out for the other two categories. Okay, so it's kind of like a box plot. They're talking about Q1 and Q3, but they left off the rest of the box plot. They did mention the middle 50%, as we've talked about before. So there's variation, of course. So we can talk about this other stuff. And the equation of thumb equals height two groups, split into two parts, plus other stuff. What is the x variable? What are its possible values? Okay, well, yeah, you've got the explanatory variable is the original one, height to group. So we're trying to use the height divided up into two pieces to predict the length of the thumb. But that's not nearly as good as we just saw. This one's a little bit better. We've got the three groups, which was done next, and it's better than the first. But this one is by far the best one we just did. It has all the data of the height. And even though it's not a perfect match, it does provide quite a bit of information. And what's the explanatory variable? Whatever follows the equal sign. Height is explanatory, height 3 group. All the heights are the x values. And the y on the left side, like y equals mx plus b, is the outcome variable. What are its possible values? Well, you could take a look at the groupings here and pick out a few of them. Here from about 40 to about 80 for the short group, and you can find the others and just fill it in. Okay, thankfully we're almost at the end of this long section. We can try to explain variation with categorical explanatory variables such as sex and height 3 group. We could also try to do it with a quantitative numerical explanatory variable, x variable, such as height, which is my favorite way to go. Let's stretch our thinking further. What if you wanted to have two explanatory variables? We did look a little bit at that before with the Happy Planet Index. And so you could take both of them into consideration, talk about thumb length in terms of the gender and the height, and of course miscellaneous. And that could be done too. It's multi-level. Yeah, so you could see if that would help. You've learned many R functions that could be used, and on and on and on. Let's just look at this summary here. And single categorical variable, in this case, which visualizations could you use? And so here's one I probably ought to let you work on, but the way I got it was the tally and the GF bar seem to be pretty good for this. That's the categorical variable. Here we have a quantitative variable. So it looks like the other ones, this is pretty much the same list. It looks like the C and the D would work there. But as I say, I should let you do it on your own and play around with it, see when you get it green or not. And then we have a categorical outcome variable, Y, a categorical explanatory variable. They really get into this stuff much more than I ever have. The tally is the only one that seems to make sense here, and that seems to be the crudest way to go, but that's all you got when everything's categorical. And now we have quantitative and categorical, and that one turns out to be everything else but tally. All the others are fine. And then we have the numerical outcome variable and quantitative explanatory. So they're both numerical, and one of them's X, one of them's Y. Which visualizations could you use? It looks like I'm getting D and E for that one. But anyway, they've got a long table here, just in case you needed to know this stuff. They've got everything all done, and so this is a list that you can certainly take a look at. I'm not going to talk about it too much, but it's kind of a summary of what they just went through. In fact, you could use some of these to answer some of the prior questions if what I told you went too fast, or if you're just trying this on your own and checking me out later, which is always a good way to go. We always hope that some of you are working on this before you watch the videos or before you come to class, so to speak. And notice one of these has not been covered yet. So when X is numerical and Y is categorical, that has not been covered. Let's move out of this section and try 4.9. This is a short one, so let's make some work of this one. We now have a sense of what it means to explain variation in an outcome variable with an explanatory variable. And we visited briefly the idea that if we add more X variables, we can reduce the amount of variation that is unexplained. We could dig a little deeper, and this is some of the theory that they enjoy so much. Consider the following case. Children who wear larger size shoes score higher on standardized academic tests than children who wear smaller sizes. Researcher A recommends that parents buy their children larger shoes to promote academic success. So, does larger shoes make people smarter? I don't think so. Anyway, the outcome variable, the Y, would be the success, the academic success. What's explanatory variable? The larger shoe sizes, or simply the shoe size. What would be a good visualization to look at this data? Well, you could do any one of the others. I would just do the dots with the multi-levels, the scatter plot, the quantitative versus quantitative is what I would pick. Researcher believes that she has explained the variation, so we've gotten some sort of connection between the large shoe sizes and the academic success. But it isn't true. Turns out this is a kind of a false lead, and so the whole thing kind of falls apart because it doesn't happen to be true. It's true if it is true, it's because of some other reason. But they're picking some of these straw man arguments on purpose just to kind of see how you do with it. This is more like a logic class than a math class at this point, but I like logic sometimes. It says average temperatures were much higher in years when more people wore t-shirts, shorts, bikinis, and other garments that exposed lots of skin to sunlight. So this researcher says global warming can be combated by dressing more modestly. So if everybody wore a coat and a sweater, the weather would cool down. Okay. I'm not sure what country that's in. But according to the researcher, what's the outcome variable? Well, apparently the global warming is the outcome variable, or the temperature, the overall temperature, you could say. The explanatory variable would be how you dress. How much clothing do you wear? You could put a quantity on it, maybe the pounds of clothes you wear, something like that. Another good visualization, I'd say the quantitative versus quantitative is always my favorite. That's my particular set. The researcher believes that he has explained variation. Was explaining to him, I'm not quite sure what they're getting at here, and I don't think this has very much to do with the class, but I would just have to say they're trying to connect the two situations. They're trying to say that people wearing different kinds of clothes controls the temperature, which of course is not true. And yeah, this is simply not true. Just think about it. It doesn't make any sense. They've reversed something that may be true. When it gets hotter, people wear less clothing most of the time. That not the other way around. X goes to Y, not Y goes to X or whatever. So the problem of inferring causation, we've used the word explain to mean that the variation in one variable can account for variation in another variable. Put another way, unexplained variation is the Y variable reduced when the X variable is included in the model. So they go into a lot of stuff, and I don't really intend to read the whole thing to you. You should read it yourself. But sometimes you're looking for a causal explanation, which may or may not be true. The examples above introduce two specific problems you run into. The direction may be not what we assume. So the second example for B is really the other way around. And yeah, people do wear skimpier clothes in hotter weather, but it's the wrong direction. And the second one is problem of confounding. Researcher A has found a pattern. Shoe size seems to lead to academic achievement, but it's possible that neither one of these variables cause the other. It might be a third lurking variable, a C, instead of A and B, that a third variable not measured in our study causes both the shoe sizes to increase and the academic achievement to increase. So what confounding or lurking variable might cause increases in shoe size in the test scores? I would say that because bigger children wear bigger shoes on average, and they tend to be older and tend to do better. So if you have a 5-year-old taking the same test as a 10-year-old, who do you think is going to win almost all the time? You get a higher score, the 10-year-old, of course, and of course they have a bigger shoe size. So this would be some sort of standardized test that lots of people take, not just 1 year at a time, but maybe a group of 7 or 8 years at a time. And so, of course, the younger people won't do as well usually as the older people. And of course, the shoe size goes along with that. Okay, may not care about causality, and we do care usually what causal relationships are. That's at least in this class we will. We won't be satisfied until we've identified the causes. And so this is where adding lots of variables in tends to help, but sometimes if you throw in some crazy variables that don't matter, then it becomes not too cool. So research, designs, and causality, so lots and lots of reading here. So these are intentionally silly. So yes, they did. Mitch mentioned that. One of them was a directionality problem. One of them had a lurking variable. and they kind of repeat themselves just a little bit. But we're talking about a correlational study or observational study. We just measure them, and they talk about a famous statistician, the father of experimental design. And so here's another example they're going to talk about. So this person draws a smiley face on a check, gets a huge tip. Has she proven a causal relationship? No, she hasn't. A particular table may have had generous tippers, or the food may have been exceptionally good, and maybe it has nothing to do with the service. But we'll talk more about this as we go along, and this is called experimental design. And so the beauty of random assignment tends to smooth a lot of those things out. So random assignment says that we can either put a smiley face on the check or not put a smiley face on the check, and we mix them up a little bit. So essentially what we'll have here is that we'll have the first one, the random sampling, meaning the process of making a selection from the population without bias. That's just what we've generally talked about before. But this new one, random assignment, is the process of choosing also without bias whom from your sample will be in different experimental conditions. And normally you don't want to cherry pick people that go in group A or group B. That's just not going to happen. So it is done randomly. So you'd submit that. A little bit more here. These things that never seem to end. The beauty of the random assignment, practically done, randomly assigning cases into a study into one group or the other. We are in essence constructing two groups that are comparable to each other, and any difference is completely random. So the two groups are supposed to be equivalent, except for random chance differences. There will always be minor differences. The smiley face versus the non-smiley face seems to be the one we care about the most. And there could be lots of other variables that explain it. Could be the weather, could be lots of things. Maybe somebody just made a lot of money in the stock market or just lost their job. There are all kinds of things you could put in there. Let's say a table's filled with people who are celebrating an occasion tend to be more generous than people who are not celebrating anything. So how would this help? That would just be a kind of a confounding factor, as it turns out. So if you randomize those types of people, then that kind of difference is smoothed out. And we have no reason to believe there'd be any more in one group than the other. And then we isolate the factor that we're interested in, the smiley face. And they say that here. Generous table is no more likely to be assigned to one group than the other, so it kind of gets split 50-50. And so we don't have to worry about that too much. Of course, the bigger sample size, the better. But confounding variable could still be in there and have some effect. But the more people you put into a sample, the better off you would be and less likely you would have to see that kind of a thing. Let's see how far we can get into the final section today. It's 4.10 called Fooled by Chance, the problem of a type 1 error. I know this is a long lecture, and I just happened, by the way, to do 3 versions of my last lecture for my other class because I had technical issues. So I had to do that lecture 3 times before it finally took. I certainly hope this is not one of those. I'll be back to doing live all the time, which has some advantages and certainly some disadvantages. But anyway, let's see how far we can get through this before I lose my nerve. Fooled by chance, the problem of a type 1 error. Let's take a break from this praise fest, which is what it sounds like to me, for the random assignment experiment and talk about why we might still be fooled even with the most powerful of all research designs. Let's say we do an ideal experiment. Everything was done very carefully by the book. We assign tables of eaters randomly to one of 2 groups. Tables in the experimental group with the smiley face, and then the other group do not get the smiley face. Other than that, they're all just typical people. And we measure the tips and see what happens. Based on this information, do you think drawing a smiley face causes servers to get higher tips? I'd say maybe, because it might put them in a slightly better attitude, but I think the difference is a lot smaller than you might think. It may not be worth your ink in your pen. Significant versus practical differences sometimes get around. Now, the smiley face was not the cause of higher tips. Could have been all kinds of other stuff, but it would be done randomly, though. We wouldn't really be able to isolate that. So you'd come up with a word equation. I will let you do that. Pick your y, pick your x, and put the other stuff in. If this is perfectly done, there are 2 possible reasons why the smiley face group got bigger tips. First, most interesting reason is there's a causal relationship between the face and the tips. That would be cool if a little drawing really does make a difference. And I've heard it does make a small difference, but it tends to be a small difference. So in case anybody's in the biz, you can do that. And I expect an extra 15 cents or something like that. I'm not exactly sure what the numbers are. It probably varies. But they've got random variation, as we keep mentioning. So in the random assignment, we say any difference in an outcome is a result of random choice. And so we it's still there, but it's not as prevalent if we spread it out amongst 2 or 3 different groups. So there's 44 restaurant tables, and you've got the numbers, the table ID, and here's the tip amount. That's a pretty big tip. Must have been a pretty big group of people, and so they've just gone ahead and given us that. So you put 22 tables in one group, 22 tables in the other group. The distributions of tip would not look exactly the same because of random choice, random chance. That would just, you would change things around a little bit. Make histograms in a facet grid of tip by the random groups 1 variable from the data frame tables. Let's see what we can come up with this one. So they did say density histogram, so I know how to do that. That's GF da histogram, GF underscore da histogram. Not having any luck today. Hopefully this will work out better. And if we put in the variable as tip, and then we put in data equals tables. So finally we have a different data set. That's nice. I'm getting tired of fingers. And they did say from the data frame tables. Okay, and then we can kind of chain that. Of course, that's the percent greater than percent, and typically go to a different line. And then we can go to the facet grid as they suggested. That kind of lines things up for us numerically. I'll type in facet underscore grid. And next we could put in random groups tilde dot. So random and then groups and then tilde dot close parentheses. And I got to capitalize random groups because that's how they did it. And it's also random groups 1 because every subtle difference makes a big difference. Okay, let's see what happens when we run that. Ah, it worked. So happy to see that. And yet, of course, a bigger, better example is down here. So let's focus on that. First of all, we have the tip amount. And then we have random assignments. This is just to show you how things get done randomly. You can forget the smiley face now. This is just randomly done. And we see that they're roughly the same. Roughly. There's the outlier over there, I guess. Notice the groups look different. This is definitely randomness. We look at these 44 tables, did the whole thing again, randomly assigning them to group 1 or 2, and we try it again, just for fun. In fact, we even have a shuffle command that lets us do that. So, yeah, okay. Tables, $ random groups 3, and here we can point the arrow from the shuffle command. That's going to be, I'm just going to copy this, so I don't have to type the whole thing, and I'm just going to paste it right there, and V. And I'm shuffling tables, $ random groups 1, so we just get a different look at the same kind of a thing. So let's see. In fact, they wanted us to print a few lines of that, so the head command is good for that. So head and then tables. So let's run it and see what we come up with. Okay, so we have the first 6 people. Looks like they're the same as before. But now the random groups are a little bit different. We already had the first one, but now we have a couple more, and these don't exactly match. I'm not quite sure why they don't exactly match, but anyway. We have 3 separate random groups now, and we can then continue with another one. Do you think the distributions will look the same? No, they shouldn't look the same, and they're all a little bit different. They all have different types of randomness, so they're just trying to make a big deal out of that for now. Go ahead and make tip paneled by group histograms for the next couple of situations. And so we could try doing that. Let's see, looks like create density histogram. See back here, we did the tables random groups. So here, looks like if we just did GF to histogram, because that's what they're asking for, to histogram. And now we're going to have to put tip in again, so it's looking similar to before. And then we'll say the data equals table, so that's exactly the same way as we started it. Close up the parentheses, chain it with the parenthesis of the percent greater than percent, and you can go to another line, probably a good idea. And once again, GF facet underscore grid, and then we can go to what they call random groups 2. Random groups 2 tilde dot, which is the same as before. It's like a ditto mark. So I think that should do it. And I put this number 4 goes with number 3, by the way. Let's go ahead and run it, see what happens. Okay, we have a couple of different bar graphs, histograms, and these are about the same as before. So there's random assignment number 2, divided into one group and divided into a second group. Okay, wonderful, more randomness. They're just doing the same thing. Here's number 3, more randomness again, not any particular pattern to decide what's different about them, and they put them all on a group. And luckily, we don't have to worry about doing that on the R. But we can see how they all look about the same. There's not too much to choose from there. Do the groups always look different? Yeah, because of randomness. They do look different. What do you think that is? Because of randomness. How different do you think they could look? Well, if you want to get to the extremes, it could look quite different. But usually it stays roughly the same. Okay, they're different because of random chance. And finally get back to the real tipping experiment, something that I've been trying to get to. And we have control as one, smiley face or control. So control is no smiley face. And here's the tip, and so we have first tables along with their tip and all that kind of thing. So here they've gone ahead and done it, and we can see now the difference. Control, no smiley face, and here's the smiley face. And for sure, some of the outliers, some of the big tips, had the smiley face. But is that luck? It does look like maybe it moves slightly to the right, but is it significantly to the right? It's hard to say. This is a tough one. We observed some difference in the distributions across the groups, but we observed differences even when there had been no intervention. So how do we know if this difference is real or if it's just random? That's always a tough call, or can be. Like here, it is definitely a tough call. Sometimes it's not a tough call. But how distinctive would it have to be? So there's all kinds of statistics for this. I wish we had time to actually talk about them, but no, we have to talk about programming instead. So it will illustrate some items very visually, that part is very nice. I just wish we had time for more techniques that we could show you, but we won't probably have too much time for that. It's called a type 1 error. It's when we conclude that some variables we manipulated, the smiley face, had an effect, but it didn't really have an effect. It was just due to randomness. That's a major type of error. It's also called alpha. Here's a video that you can see. I've found that it does not take audio, so you will not be able to hear it if I play it. So this is your assignment. Not only work through this on your own, but to watch the video. And so she does talk about the way it goes. And so one of her favorite things is and this is the author, of course, who does the videos. She says that tips is equal to smiley face, of course, in numerical terms, plus the other stuff. And that does seem to be what they're looking for. So this is how we could put the model of the process to be supported. And tips equaling other stuff is stupid. Both models no. B doesn't make any sense at all. Neither model will. At least it says B is wrong. But A, which they show on the video, is clearly the answer there. So now we get to this following model, which we just talked about. Where would the sample variation go in this model of the DGP? Well, the sampling variation does go in the miscellaneous or other stuff. Yeah, not really in the other two. Later, we'll learn how to reduce the probability of making this type of error. And there's also a type 2 error. I'm not sure if we'll have time for that, but it's not as popular as the type 1 error. So just be aware of it. You can never reduce the chance of a type 1 error to 0. There's always some chance you might be fooled. So that's can be frustrating. You're never completely 100% sure. Okay, that'll do it. It's been a long day of me lecturing here. I've been going at it for about 2.5 hours, so I'm done. I hope that made some sense for you. Be sure to go through this on your own. And if you have questions, please drop by the office hours, send me emails, and I'll be happy to respond to them. Trying to get those tests graded. You guys are up first. Should be done pretty soon. The middle of next week, I'm thinking, maybe by Thursday for sure. So I will talk to you later. Have a nice day. Bye-bye.